take a minute to look at this graph and see what you notice. You might even want to pause the video for a few seconds and just make sure you understand what the graph is saying. Okay, you paused the video, maybe you came back now, and you noticed that this graph is about a hospital. It's about the number of deaths that occur each shift in the hospital by year and by shift. So like out of all the evening shifts, or all the night shifts in 1988, there were about 11 deaths. And out of all the day shifts in 1988, there were probably about 15 deaths and so forth. So not necessarily a lot per day, but for the whole year. Something else you might notice is that there were certain shifts that seemed to have a whole lot more deaths than others, and it seemed to be in these middle years from 1990 to 1996, fewer deaths before 1990 and after 1995. And certain shifts, particularly this evening shift here from 1991 to 1995, had a fairly high number of deaths. So why was this? The hospital started noticing this unusual trend and started investigating. As a matter of fact, there were some nurses that were concerned about a particular nurse that they worked with, because it seemed like when she was on shift that there were a lot more unusual activity with near deaths and deaths than there were when other nurses were on shift. Her name was Kristen Gilbert. She worked at the hospital from March 1990 to February 1996. That's where you saw those big spikes in the graph. These data are from the last 18 months that she worked at the hospital when they started investigating her. So notice what the graph, this table of data shows. It tells the number of times that she was working on shift, when she wasn't working, total number of shifts, total numbers of deaths that occurred on all of the shifts, and when she was working and when she was not working. So let's do some investigation with probabilities. When you're dealing with numbers, different size groups, and numbers that are kind of messy like this, that are not easy to interpret, we want to always go to probabilities or percentages to do comparisons. To make it easier on ourselves, let's use variables to name two events. We're going to name one event that a death occurred on the shift. And G is that Gilbert worked on the shift. Now we're going to be investigating some probabilities. So let's first of all, what is the probability that a death occurred on a randomly selected shift? So remember, it's the total number of things we're looking for, the total number of the event that we're looking for over the total number of outcomes. So the event we're looking for is that a death occurred. That would be, there's 74 of those. The total number of outcomes or shifts is 1,641. So 74 out of 1,641 is not an easy fraction. If that fraction was 1/3 and we could say 1 out of 3, that would be easy. We could just leave it as a fraction. We don't want to leave one like this as a fraction because it's much more easy to interpret as a decimal or a percent. So on 4.5% of the shifts, or with a probability of 0.045, there was a death on the shift. Okay. Now what's the probability that Gilbert was working on a particular shift? So she worked 257 out of the 1,641 shifts, or on about 15%, a little more than 15%. So about 15.6% of the time she was working on a shift. Now what is the probability that both things occurred, that a death occurred and Gilbert was working? So where does that occur? We notice right here, death occurred and Gilbert's on the shift. That only happens 40 times. So the probability that death occurred and Gilbert was working is 40 out of 1,641, which turns out to be or about 2.43% of the time. Okay, so that was pretty rare that she was working and a death occurred at the same time. Now, what's the probability that a death occurred given that Gilbert was working on a randomly selected shift? This is the key question. The previous question makes it look like, oh, that really doesn't happen very often. But that's not the right question to ask. Because Gilbert was just one nurse, so she didn't work, you know, she only worked on 15% of the shifts. And if she only worked on 15% of the shifts and deaths didn't occur on every shift, it made sense that there were only 2% of the shifts where she was working and a death occurred. But let's investigate something slightly different. We're going to look at this term given. What is the probability that a death occurred given that Gilbert was working on a randomly selected shift? So when we see this term given, we're saying we're only going to look at those shifts, the ones where she was working. And then we're going to compute the probability that a death occurred while she was working. So probability of death given that Gilbert was working. So this little vertical bar is the symbol for given. So out of all the shifts she worked, so our total number of outcomes is now 257. Okay, so that's our given. There was a death occurred that on 40 of them. So this turns out to be 0.155, or about 15.5% of the time. Now the fact that this is 15.6 and this is 15.5 is just coincidence. They really have nothing to do with each other as far as computing the probability. It is important to give several decimal places, so if there are slight differences in things, you'll be able to notice them. Now, this thing that we just computed has a special name. It's called a conditional probability. The probability that one event occurs given that another event has already occurred is called conditional probability. In this case, the condition was that Gilbert was working. So we say probability of D given G. That's the given part. Two events are, now what's important with the conditional probabilities allows us to determine if some events are related. So two events are independent, and independent means not related or not associated. If the occurrence of one of the events does not affect the occurrence of the other, the probability of the occurrence of the other. So for example, if we have two events, A and B, we can say that the probability of A equals the probability of A given B. In other words, if I find the probability of A, and I also find the probability of A given that B has already occurred and they're exactly the same, then B does not affect the probability of A. They are independent of each other. And we can also do it the other way around. We could say the probability of B is equal to the probability of B given A. So one event does not affect the other. That's what independent means. So let's look at the two events that we were looking at with the Kristen Gilbert situation. Are the events death occurred, D, and Gilbert was working, G, independent? So we're going to use the independence test. We're going to say, is the probability of death given that Gilbert was working equal to the probability, actually let me write it the way I have it up here. What is the probability of death equal to the probability of death given that Gilbert was working? In other words, does the fact that Gilbert was working change the probability that a death would occur? So the probability of death we calculated was 0.045. The probability that death occurred given that Gilbert working was 0.155, a clear and fairly large difference, a difference of about 10%. So what can we deduce from that? The two events are not independent. there appears to be a relationship between a patient dying and Gilbert being on shift. So there appears to be a relationship, I think I'm going to call it the death rate, a relationship between the death rate and Gilbert being on shift. So what's the rest of the story? Well, the rest of the story is that Kristen Gilbert was a serial killer. Kristen Gilbert liked to look important by injecting a drug into patients to cause them to go into cardiac arrest and then resuscitating them, making her look like a hero. Now, of course, it didn't always work, so some of them died. There was also a factor that her boyfriend worked at the hospital, and he was on the team of medical personnel that would come to resuscitate a patient that has gone into, whose heart has stopped. And so she could also show off in front of her boyfriend by doing this. It started out with that. She wanted to look important, so she would manufacture these imaginary crises. Well, she would manufacture a crisis by causing one, and then showing off by how calm and cool she was under pressure and how she could save people's lives. But it also, but she did more than that. Sometimes, one time she killed a patient just so she could go home early because that was the only patient she had, and she figured if they died, then she didn't need to be there. And so she just killed them. I forget exactly how many deaths she caused. You can Google Kristen Gilbert, nurse, and find the whole story online. So it's pretty interesting. But this is a case where some statistical analysis actually caused them to dig into this problem. This does not prove that Kristen Gilbert caused the deaths, but it did prove that there was something worth investigating. There was an indication that there was an association of some sort, and then they found other proof that she actually did cause patients' deaths.